All right, so yesterday we started talking about integration by trigonometric substitution. And I just want to recall kind of the work that we did without using the bad chalk. Now let's just make a little chart, and maybe we'll add a little bit to the chart and discuss a few things and maybe clean up a little work that we did. So we started by considering the following: the square root of a squared minus x squared. And remember, through all this, a is always greater than 0. And we said if we're going to see this in an integral, then we're going to want to make some sort of substitution. And the substitution is to replace x by a times sine of theta. And what we showed is if you let a equal sine of theta, then this expression, square root of a squared minus x squared, reduces to a cosine of theta. And then, of course, since we're talking about derivatives usually, well, we can see that dx is equal to a cosine of theta d theta. And so this is useful because now we can replace all the things in some integral that we were talking about. So for instance, yesterday, what we looked at the square root of x squared, the integral of x squared over the square root of 9 minus x squared. And so using this chart above, it's very easy to rewrite this expression. The x squared becomes a squared sine squared. Right? The dx becomes a cosine of theta d theta. And the square root of 9 minus x squared becomes 3 cosine. Well, I guess a is 3 here, so we don't need to put a's. Right? So we get 3 cosine of theta. Okay, so all this is just coming from this chart. Yeah, this is all coming right from here. Right? We can use this every single time. Right? Whenever you have a square root of this form, you can use this substitution. Yeah? Right? And everything in here, right, we just got by looking at this chart. The x squared, well, we looked at x. So it became, when you square it, you get a squared, or in this case, well, a is 3, so you get 9. Okay, 9 sine squared. The square root of 9 minus x squared, right, comes from here, 3 cosine theta. The dx, right, became a, or 3 cosine theta d theta. Okay, all just comes right from there. Very nice. And of course, from here you can simplify. Right? You can cancel some things out, pull out a 9. And then we use this formula. We computed the integral of sine squared in class, right, independently of this. Right, and this was a half theta minus sine of theta cosine of theta. And then, of course, we'll need a plus c, but we can put that on the outside. Okay, of course, I can put this 9 in and make it 9 halves. Now, of course, you're not done at the end because you need to know what sine, you don't want thetas in the end, right? You want x's. So it's good to know what sine of theta and cosine of theta are. And typically in these problems, you're always going to get to a point where you end up with, well, an expression in terms of thetas. You've gotten rid of all your integrals, and you need to turn them back into x's. And all the expressions that involve trig functions, right, of course, they can be reduced to sine and cosine. And if you do that, it'd be really nice to know what sine and cosine are. So in addition to this list, right, that we do for the substitution, let's also write down sine and cosine. So here it's very easy. Sine is just x over a. about cosine? Well, here again, cosine is very easy. It's just the square root of a squared minus x squared over a. And, well, sometimes it's also nice to write down theta, since, for instance, it shows up here. So we actually have some choices how we can write theta. Yeah, Kaiwi. Oh, yes, it's written backwards. Thank you. Yes. So theta we can get, for instance, from the top line. If sine of theta is x over a, take arc sine of both sides. Of course, we can also do arc cosine, and it would just be a little nastier to write down. So that tells us here we can write 9/2 arc sine of x over 3 minus, let's see, sine of theta is x over a, and cosine of theta is square root of a squared minus x squared over a, so we get over a squared. Oh, a here is 3. So 9, and this is 3. 9. So there's 2 of them. Okay. And then we move the 9 in to kill some things. But okay, I don't want to do this again. Okay. So sine of theta is, divide the a, you get x over a. Chris.
How did you get from the integral sine squared of theta
To this? I used what we did in class. Okay, we proved in class in the integration by parts section that the integral of sine squared. What's that? We did it using integration by parts exactly. We said u equals sine of x, dv equals sine of x dx. Right? And when we got through it all, we ended up with a formula. A half x minus sine of x cosine of x plus c. Right? And if you want to do this again using integration by parts, that's an excellent idea. Just sit down and do it. It shouldn't take you long now. Right? Remember, you used Dina's trick. So that's how we got that. All right, so but this table is very nice because it contains basically all the information that you'll need in this case. Let's do a different case. Let's do the square root of x squared plus a squared. So in this case, we saw that the correct substitution was a tangent of theta. Right? This ended up utilizing the formula tangent squared plus 1 equals secant squared, which we wrote down slightly incorrectly. It must have been Kaiwei's fault. Okay. Once you make this transformation, then we saw that this expression becomes a secant of theta. And since you always are talking about this in the context of integrals and derivatives, okay, we should write down dx, and dx is an a secant squared theta. Okay, so this is really nice because it means given an integral that has something like this in it, there's a very good chance that we can rewrite it in terms of thetas. There's a d theta missing. In terms of thetas, just by using these 3 rules here. And they all come from this first substitution. Right? These 2 you can derive from this. Okay. Now, we saw over here that after you work the problem, in the end you get some integral that oftentimes will have sines and cosines, or it may have some other trig functions, but as long as you know sine and cosine, you can get the rest of the trig functions. Okay? So let's try to figure out what sine of theta and cosine of theta are. Okay, to do this, we need to use this right triangle trick. So well, let's just do it on the side here. So tangent of theta is x over a. Which is the same thing as saying that the inverse tangent of x over a is equal to theta. Just take arctan of both sides. Which means that sine of arctangent of x over a equals the sine of theta. Yeah, just take sine of both sides. Okay, so if I want to know sine of theta, I can compute this. So the way I do this, I draw a right triangle. I put a nice angle theta in there. And first thing I look at is I say, okay, I have some angle such that the arctangent, right, of x over a is theta, which means that the tangent of theta is x over a. Right? Which means, well, if the tangent of theta is x over a, then the opposite over the adjacent, which is what the tangent is, should be x over a. The tangent of this angle is now x over a. That's what we want. Okay, I can compute the hypotenuse using the Pythagorean theorem. And now if I want to compute the sine of this angle, I just do the opposite over the hypotenuse. So sine of theta is, well, the opposite is x over the hypotenuse, which is square root of x squared plus a squared. And, well, this is really nice because it also tells me what the cosine is. The cosine is just the adjacent over the hypotenuse. So a over the square root of x squared plus a squared. So I can fill these in now. I could do a theta here. I just have to choose either the arc sine of the top or the arc cosine of the bottom or the arctangent of x over a. So maybe I'll choose that one because it's somehow the simplest. All right, so this gives me a setup for the square root of x squared plus a. Incidentally, if you don't like the right triangle trick, even though you should because it's really pretty awesome, another way that you could have gotten sine out of this is to note that tangent of theta divided by secant of theta is, well, this is sine over cosine divided by 1 over cosine, which is equal to what? Just sine, right? This flips over and you get just sine. Right? And of course, nothing changes if I put an a here, because they'll just cancel. Right? So sine of theta is a tangent of theta divided by a secant of theta. But right, a tangent of theta is x, and a secant of theta is square root of x squared plus a squared. Right? Okay, so this is not so bad. Yeah. So there's some options, but in any case, this way works nicely, and boom, you got it. Right? You can even write these formulas down if you are so inclined. Okay, so I think we had an example that I can't remember if we finished it or not. That's right. We got to that. That's right. We reduced it to that point. That's right. Yeah. So let's just transform the integral. So we had the integral of the square root. Wait a second. I must have that wrong. Yeah. It was the 4 plus x squared to the 3/2 power. Right? So we rewrite this. The dx becomes a secant squared theta d theta over, well, let's see, 4 plus x squared. All right, forget about the 3. This is the square root of 4 plus x squared. Right? And, of course, you have to cube it at the end. But when you have the square root of 4 plus x squared, you use this transformation, right? And this becomes, well, a here is 2, so 2 secant of theta, and then you have to cube it. So you get 2 cubed secant cubed theta, which was 8 secant cubed theta. Okay. Oh, I guess this a is still 2. Okay, and so then we simplified this quite a bit, and we ended up with this integral of cosecant that we didn't know how to do. And we still don't know how to do it. Oh, is it for the other one? Oh, okay, what happened for this one? We got a fourth integral. Okay, you get 1 over secant. You just get cosine. Yeah, this one's not bad. Yeah, you just get 1 over, you just get cosine, yeah? Of course, what's the integral of cosine? Sine, right? Because this says whose function's derivative is cosine. Yeah, so it's sine. And now you can see why it's nice to know what sine is. Now we can just immediately resubstitute our x back in. Okay. You'll find this is, typically the case when you do these trig substitution problems, that your answer is going to involve sines and cosines or another trig function, but once you know your sines and cosines, it's okay. You can do the rest of them. So this just becomes a fourth x over the square root of x squared plus 4 plus c. Okay, and then the last transformation. Right, well, we just tweaked the second one a little bit. We put a minus in there, and when we put the minus in, it just swaps the tangent and the secant. Bless you. Nobody knows why I said that now, because they can't hear the sneeze on the tape anymore. That's great. Okay, so when we have square root of x squared minus a squared, like I said, we're just going to swap the role of tangent and secant. Right? It's really the same thing going on. You just do a minor swap, this little transposition. Right? And of course, well, the derivative gets slightly longer, because the derivative of secant is now secant tan. And what we've seen before, it's good to know sine and cosine, so let's try to suss those out. So, well, why don't we just try this triangle trick again? Let's see. We know that the secant of this angle, theta, is just x divided by a. Now the secant is what on the triangle? It's 1 over cosine. Now cosine was adjacent over hypotenuse, so 1 over cosine will be hypotenuse over adjacent. Right? So the hypotenuse over the adjacent is x over a. So the hypotenuse over the adjacent is x over a. And now, by the Pythagorean theorem, we know this last side is the square root of x squared minus a squared. Notice the nice symmetry that these things create. It always seems to work out. Okay. So now what's the sine of the angle? Well, it's the opposite over the hypotenuse. So the square root of x squared minus a squared over x. And the cosine is the adjacent over the hypotenuse. So nice a over x. And if we want theta, well, we actually have there's a couple easy choices, right? Secant is x over a, so theta could be the arc secant of x over a. Cosine is a over x, so theta could be the arc cosine of a over x. 6 of one, half a dozen of the other, right? Okay, I'm going to go with the secant, and I'll tell you why. Normally, I don't like to use secant if I can use a cosine. But somehow it's nicer to have a constant in the bottom. I don't know why I think that. It just feels wrong to have the constant on the top and the variable on the bottom. So we'll go with the arc secant. You know, it needs love, too. Okay, so this I don't think we got to yesterday in here. Is that right? This last bit? Okay, good. So then let's work a problem. All right. So let's try integrating the square root of x squared minus 16 over x to the fourth. Why? Because we can. It's there. All right, so what's my transformation? Well, kind of fits under this part of the wall, so that's probably this one. Right? So the x is going to be replaced with, well, a here is 4, right? Square root of 16. So we're going to replace with 4 secant of theta. So let's rewrite this. So, well, this top bit is really easy. That just becomes 4 tangent of theta. Right, then we divide by x to the fourth. So x is 4 secant of theta. So to the fourth power, well, let's see, we're going to get secant to the fourth. And then we need to know what's 4 to the fourth power. Very good, 256. 4 to the fourth, same as, well, 4 squared squared. 4 squared is 16. 16 squared is 256. Or 2 squared to the fourth, which is 2 to the eighth. 2 to the eighth is 256. Okay. Now we need the dx. And the dx is, let's see, 4 secant of theta, tangent of theta, d theta. Dina, you're moving your lips like this. Okay, good. Ah, yes, so we're starting with x to the fourth in the denominator, but we're making a substitution. X is going to be 4 secant of theta. So I just take that to the fourth power. Then, there we go. See, what's that? When I say I read lips and go. See, you don't even have to raise your hand in my class. Just do a funny face and I'll know you're upset. Okay, so now we try to simplify a little bit. So we have a 4 and a 4, that's 16, divided by 256. So 16 divided by 256 is, remember 256 was 16 squared. So it's just 1 over 16. So I can pull a 1 over 16 out. Now let's see here. I have a tangent and a tangent. That's a tangent squared. And I have a d theta. And I have 4 secants on the bottom and 1 secant on the top. So I'm left with 3 secants on the bottom. Okay. Now, we could try replacing tangent squared with secant squared minus 1. Right? And then we'd have secant squared over secant cubed minus 1 over secant cubed. But then we'd have to compute the integral of cosine cubed in the end, which is kind of a hassle. Okay? So let's try a different approach. Remember over here, we actually saw what happened when you divide tangent by secant. You get sine. So, well, here you have 2 tangents and 3 secants. So if you just pull out 2 of the secants, you'll have tangent squared over secant squared, which is what? Sine squared, right? Because if you have 1 of them, it's sine. So if you have 2 of them, it's sine squared. And then you have 1 more secant cubed on the bottom. Right? Of course, 1 over secant cubed is 1 over secant rather, not secant cubed. 1 over secant is cosine, right? So this is actually 1 over 16 times the integral of sine squared theta times cosine of theta d theta. And what do you think would be a good way to attack that problem? Substitution. What would be your substitution? You can do that, and you're going to end up with a sine cubed. Right? We're right back where we started. What about a real, when I say substitution, I don't mean just to replace this by, do a U substitution, right? What would be a good substitution for this? Well, remember, substitution is usually working when we have a composition of functions. All right? Remember, the substitution corresponded to the chain rule. So we have a product of functions, but then one of these functions is actually a composition of functions, right? It's sine of theta squared. Right? It's a composition of the function sine of theta and the function x squared, or theta squared. When do we have till? 11:15. Okay, good. So remember, you usually want to do your U substitution where you have the composition of functions. So what should be my U? Sine theta. Okay, so we'll try that. We'll try U equals sine theta. And of course, if we do U equals sine theta, then du is cosine theta d theta. Okay, so this thing can be rewritten as 1/16 the integral of, well, let's see, sine squared is now U squared. And cosine theta d theta is, just du. Look at that. How clever we are. Okay, so now, the integral of U squared is 1/3 U cubed. So we end up with 1/48 U cubed plus C, which is 1/48. Okay, U is sine, so we get sine cubed plus C. All right, we have to unravel all our substitutions. Right? Now the sine theta, see, isn't it good we computed it? Square root of x squared minus, well, in this case, a was 4, right, over x. So we get 1/48. And now we have to cube everything. So let me write this as x squared minus 16 to the 3/2 over x cubed plus c. Whew. We have just enough board space. Nasty. Nasty. Okay, but you can see, hopefully, that it's very nice to have all of this information at your disposal, because you can just read right off of this chart. It's not, I don't want you to have to develop all this every single time. But you should be able to, because, well, it's hard to memorize a lot of these things, right? So you should be able to reproduce this. But it's really nice if, for instance, you're doing your homework, you write out a nice chart, and now you can refer to the chart as you go. Okay, it's not bad. But do try to figure, in case you're on a test and you forget, you can re-come up with this chart. Give it a shot. By the way, for those of you who have been around for my law of Co before, part of my law of co says that you only need to really know properties about sine, tangent, and secant, because you get all the co's from the original ones. And once again, right, these transformations all look at sine, tangent, and secant. So there's not a coincidence there. Okay. Any questions? Yeah. We don't know how to do that yet. So our next section is going to be on something called integration by partial fractions. And that is what we're going to use to integrate cosecant, secant, these sort of things, right? It doesn't seem like they should. I mean, if you've seen partial fractions before, then it should occur to you, wait, what in the world do partial fractions have anything to do with secant and cosecant? But it's going to turn out that's a good way to attack them. So that'll be in our next section. We'll be able to go back and resolve that problem. Okay, let's do another example. This one's something we already know the integral of. So what's the integral of this? Not tan, but arctan. Yes, arctan. Okay, but let's pretend we didn't know that. So which rule would we want to use here? Well, we'd want to use the second one, although there's kind of something funny going on, right? Here there's a square root, and here there's no square root in sight. Okay, we can still make this substitution, right? We just have to be careful. So let's try using the substitution x equals, well, let's see, a here is just 1, so tangent of theta. Okay. Well, let's write our things down. Then, well, if the square root of x squared plus 1, or 1 plus x squared, is secant of theta, what will 1 plus x squared equal? Secant squared. So 1 plus x squared becomes secant squared. And, well, the dx doesn't change, because that's just coming from your choice of x. Okay, cool. I can rewrite my integral as, well, let's see. The dx is secant squared d theta. And 1 plus x squared is secant squared of theta. And now this is really sweet. The secant squares cancel, and you reduce to this. Now, that is as perfect a substitution as you could possibly make. It could not get any better than that. Dina, you still look confused. Even though we did it perfectly. You're doing the lips again. Then what? Okay, well, what's the integral of d theta? It's just theta, right? And now, right, I just need to go backwards and say, okay, what is theta? Well, look at my chart. Theta is arctangent of x over, well, in this case, a is 1, so just arctangent of x. That's not too shabby. That is not too shabby. Okay, let's up the ante just slightly. Let's just make this a little more interesting. Now this is nice. This does not look like trig functions should be involved here, right? Other than, well, remember last term we saw, okay, e and the trig functions are involved in some unnatural way, but But really, I mean, why would trig substitution work here, right? These are all, these kind of weird forms. But let me rewrite this e to the 2x for you. You can pretend, right, that e to the x is itself a variable. And so you really have something like 1 plus a variable squared. So you're somehow right back into this case again, with, of course, the square root missing. But you might try it. Now, what this tells you is whatever your variable is, you set it equal to a tangent of theta. All right? Well, in this case, a is 1. And the variable is not just x, it's e to the x. So we try e to the x equals tangent of theta. Okay? It's a little strange here. All right? And then we know that 1 plus e to the x squared should equal, well, secant squared. Because we don't have the square root here. And then the dx, well, now we're careful here. If we differentiate, we don't just get 1 anymore. Now we get e to the x. So e to the x dx equals secant squared theta d theta. Okay? But of course, in the end, we're not going to want to have e to the x dx, or, well, I mean, we could actually. It's right there, so that's not so bad. Actually, we're going to be quite happy. Okay, so let's do this substitution. E to the x, oh, Chris. All right, so we start with this equation, e to the x equals tangent of theta. So if we take the derivative, all right, remember before when we took the derivative, we used to get 1 times dx, right? So that's why you're ending up with e to the x still. Things are a little more complicated. Okay, so let's see. So e to the x dx is secant squared theta d theta. And 1 plus e to the x squared is secant squared. And we've ended up in the exact same place, which is what you should expect. We've just replaced the variable x somehow with e to the x. So of course, this is nice and easy to integrate. And now we just need to see what theta is. Well, it's not quite as nice as before, because it's not arctangent of x, but it's arctangent of our variable, e to the x. Yeah? Into here? Oh, how I got this. Okay. So we'll start with e to the x. Yeah? Okay, and it equals tangent of theta. Okay. So now I'm going to differentiate. And if I differentiate, what's going to happen? On the left side, I get e to the x. Right? And on the right side, I'm getting secant squared. Okay? And now I just need to sort out where my dx's and d thetas go. Right? And, well, of course, you know that these x's should stay with the x's, and the thetas should stay with the thetas. So this is how we get to here. And if you start up here, start with x equals a tangent of theta. You take the derivative of x, you get 1, right, which is kind of hidden here. And here you get your a secant squared d theta. So you're doing the same thing. Okay. All right, so we wanted to know what theta was. Well, we know that e to the x is tangent of theta. So if I take the arctan of both sides, then I get theta. So the integral is arctan of e to the x. Right? Now let's just quickly make sure that this is correct. What would be the derivative of arctan of e to the x? Well, let's see. It would be 1 over 1 plus e to the x squared times e to the x. And that's where you get that e to the x up top. So these substitution methods are very versatile. And the way that they're usually presented at first, like this, suggests that, well, you have to have that sort of form with the square root and everything. But look for opportunities to use these things in other places, because there's a lot of really slick ways of reducing things using these substitutions.